So welcome to this video. Today we will be discussing about robustness as one of the important measures of resources in quantum information theory, and we will see that how robustness is calculated by using the dual problem of converting it into optimization of observables in quantum mechanics, and these observables will be optimized under certain constraints. So let's first recap what we know about the primal and the dual problem. So, so basically, this is the recap. So we have the primal problem, which is an optimization of this kind of an inner product under constraint that the linear map gives the output y and x belongs to k. So x belongs to a closed convex cone here. So this optimization will yield or give a value of p, which is the output of the primal problem. And the idea is this lambda, this a, and this y, these three. So the tuple lambda, a, and y, these three are fixed by the problem at hand. So given this, we frame the Lagrangian of the problem. So this is the step 2 that I have shown here, the Lagrangian of the problem, and it is given by particularly the optimization which we have to perform minus the constraints and appropriate Lagrange multipliers to the constraints. So here remember there are two constraints. One is the constraint of the equality of lambda of x is equal to y, and that constraint we put the value z, and the second is the constraint that x belongs to a closed convex cone, and for that we put the Lagrange multiplier to be q. So here q belongs to the dual cone of k, which is the cone that contains the separating hyperplanes. This I have discussed in the previous video. So given this, we get the equality from here. So here zy, I am separating the Lagrange multiplier corresponding to the equality constraint, and when I separate this, so this is corresponding to the equality, and then the rest of this I put it as 0. Basically this is a shortcut way to understand the entire algorithm of framing the dual problem, and to see what this means, there is a video that I have already made. So I put this entire thing as 0, and here lambda star is the self adjoint of the linear map lambda, which is defined in this particular fashion. And the idea is now to perform another optimization over the Lagrange multiplier z. So you have to calculate supremum over this inner product, which is now in the output space of the linear map. So you have to calculate this supremum, and particularly under the constraint that this is 0. A minus lambda star z minus q is equal to 0. So this means A minus lambda star z belongs to k star, because k star is the dual cone of k, which is the set containing the separating hyperplanes. Now z belongs to v prime, because v prime is the output space of the linear map lambda. So this gives me another optimizing value, which is the dual value, that is called d. So I have two problems, p and d, and in general the output that I get from the primal problem need not agree with the dual problem, and only weak duality is satisfied, that is d is always less than equal to p. This I proved in the previous video. But under certain conditions, so under certain conditions which are very weak conditions, so basically these conditions are very kind of trivial or satisfied in a very simple way. These conditions are conditions on the set, particularly set of primal feasible problem and the dual feasible problem. So the primal feasible set and the dual feasible set. So these conditions, if you have, under such conditions, the primal problem value and the dual problem value, they become same, and this is called strong duality condition. So strong duality is nothing but the case where P is equal to D. And for now we take strong duality for granted, and later in a video we will prove the Slater's theorem for strong duality. So now with this we have primal problem and the dual problem. So here is the primal problem, here is the dual problem. And primal problem, instead of infimizing, I have written minimizing because I will use it in a while. So you have minimizing over this inner product subjected to these constraints here. So lambda of x is equal to y and x belongs to k. And in the dual problem you have maximization over the kind of this other variable which lives in a different space, which is in turn the Lagrange multiplier, subjected to certain further constraints that I have shown here. Now you can write the primal and the dual problem in this fashion, but you can also write it in an opposite fashion where you interchange the maximization problem and the minimization problem. So this is done by making a change of variables. So change of variables. So the change of variables is lambda goes to minus lambda, a goes to minus a, and y goes to minus y. If you make this change of variable, you get the primal and the dual problem interchanged, because here you will have a minus a, in here you will have a minus a, and this minus a minimization means maximization over ax. So that I have written in this side, maximization over ax subjected to lambda x equal to y. This stays the same because I put a minus on both lambda and y and they cancel out, and x belongs to the cone. And the dual problem becomes a minimization problem because of similar reasons, and then this is the constraint, and z belongs to the output space. So again it is important to stress that these two versions of the primal and dual problem, they can be obtained by change of variables, and these variables that we have, they are fixed for certain problems, like given the problem in hand that we will see soon. So the problem at hand that we will deal with is robustness. So first I will define what is robustness. So there are three types of robustness. One is called standard robustness, one is called generalized robustness, and one is called absolute robustness. So in each of the kind of robustness, the idea is you kind of have a state rho. So let me show it here. So suppose you have the set of density operators D, and you have a convex set F, and now you have a state that has some resource. For example, entanglement is a resource, and this set F is suppose separable states. Then what you can do is, to this entangled state you can add some noise. So you add a noise, suppose that belongs here, and then this addition or the convex combination lies in this straight line, and if you generate a separable state, so what you are doing is you are putting noise to your state to make it separable. So this kind of noise exists in nature, and they are pretty harmful because they will convert your entangled state into a separable state, which will not be useful for some protocol that you may want to perform. So this criteria, that how much minimum noise you require, is what is called robustness. So the more is the robustness, the better is the entanglement of a state. So this is kind of the main idea. So the more is the robustness value, the more is your state useful for some protocol. So these robustness, there are three kinds. Standard robustness, which is how much noise you want to add from the set of free states or the set F, which is for example the set of separable states. So you take your original state, you add to it the noise. So this is the noise, and this noise belongs to the separable state. It will not be an entangled state. Now the next one, which makes more sense, is generalized robustness, which is how much noise you add such that the adding noise, the noise that you are adding, it can be any matrix in the density operator space. So this makes more sense because in nature it is not that there is there is only separable state. So you can have noise such that two entangled state are convex combined and becomes separable. And the third one is absolute robustness, which is kind of the noise you are adding is white noise, which is the maximally mixed state. So in each of these robustness, the main idea is that you are adding some noise to destroy your resource, and the more your state is robust, it means the more entanglement it has that can be useful for some task. So now we will talk about the dual problems of robustness. So in this case, the idea is we will frame the primal problem in a better way. So the primal problem is actually this problem, minimizing over R such that this thing lies in the set of free state. So this convex combination that I showed in the diagram. So the way to frame it will be, what we do is we take this constraint here, this convex combination, and we say that rho plus R tau we call it as a state which is unnormalized, and 1 plus R times a state in this free state, we will again make it unnormalized. So basically what we do is we write rho plus R tau is equal to 1 plus R times sigma tilde. And now you can see this not sigma tilde, sigma. So tau is a state which is a density matrix, sigma is density matrix, rho is the density matrix. But 1 plus R sigma will be an unnormalized state, sigma tilde. The trace of sigma tilde minus 1 will be R, which is the optimization that we have to perform. So here we have to optimize over R, right? So this means we can convert R times tau to a state tau tilde which belongs to the cone of the set F, because R is a positive number and I am generating a cone from this set of free state. So let's see this. So the main idea here is I have shown in here. So you have trace of sigma tilde minus 1, which is R basically written in a different way, such that rho plus tau tilde is sigma tilde, this constraint here, and sigma tilde belongs to cone F. So sigma tilde is generated as 1 plus R times a free state. So this is this constraint here, that my state belongs to the free state, or this constraint here. So this means that my sigma tilde belongs to cone F, and my tau tilde, it now either belongs to cone F or belongs to cone D. So if I am talking about generalized robustness, I want to make it cone D because I am adding the noise. So tau tilde is the noise. So let me write it. Tau tilde is the noise, and tau tilde is the noise, and basically you want to add the noise from the set of D for generalized robustness, which is this constraint, and for standard robustness it belongs to cone F, which is this constraint. With this primal problem, we will now construct the Lagrangian of this problem. There are two optimizing variables and we have three Lagrange multipliers. So one of the variable is sigma tilde, another is tau tilde, and one Lagrange optimization, one Lagrange multiplier is Z, which is corresponding to the equality constraint, that is sigma tilde minus rho minus tau is equal to 0. So this is equal to 0, and one corresponds to the fact that the the output that we have, it belongs to cone f. So the q, it belongs to cone f star, the set of hyperplanes kind of thing. And similarly we have w. Now w can either belong to cone f star or cone d star. So in generalized robustness, it will belong to cone d star, which is nothing but set of positive semi-definite matrices. And in standard robustness, it will belong to cone f star. So with this, we have the Lagrangian at hand, and we can simply read off now the dual problem. The dual problem is a maximization now over this constraint here, which has the Lagrange multiplier z. And z is a Hermitian matrix, so it is actually an observable, you can see, because the set we are dealing with is the set of observables. The hyperplanes, they lie in the set of observables, and we have maximization over trace z rho minus 1, this maximization, such that 1 minus z from here belongs to, which is equal to q, 1 minus z equal to q, that belongs to the cone f star. So this is always there. So this means cone f star, if you remember, it has a particular definition that I have discussed. It simply means that trace of 1 minus z sigma is greater than equal to 0 for all sigma belonging to the free state. Similarly, we have z belongs to cone d star if we are dealing with a dual problem of generalized robustness. So where the noise is from the entire set of density matrices, and here this gives that z is greater than equal to 0. This is because cone of D, cone of set of density matrices, is positive semi-definite matrices, and the dual of positive semi-definite matrix, which I have discussed in a previous video, is a positive semi-definite matrix. So this gives us the generalized robustness. So generalized robustness as this optimization problem here, maximization over this particular value subjected to two constraints like this. Similarly, you can also try to calculate the standard robustness. Here z greater than equal to does not play a role. This is because particularly I have a reduced space of constraint where the constraint is not it belongs to positive semi-definite matrix, rather it belongs to the set of free states. So you are adding only separable states to your entangled state and not any state. So this means that your constraints will change. So one of the constraint remains same, that is trace z rho is less than equal to 1 because this comes from the q condition that is here, and the other constraint is simply changed with trace z rho greater than equal to 0. So this constraint is z belonging to cone f star. This implies trace z sigma is greater than equal to 0 for all sigma belonging to f. So what I have shown in this video is that you have robustness measure, which is a measure in the space of density matrices in the set of states. So you are adding to a state some noisy state such that the noise makes it a resourceless state, and you can convert this optimization into optimization of observables, which is now in this space of Hermitian matrices, and this conversion is useful to actually show that robustness can be calculated by such a way using semi-definite programming because sometimes these dual problems are simple to solve. So with this I will end my video. So in the next video we will talk about another concept, which is mean conditional entropy. Thank you.